Right. I'm sorry that I cannot be there today in purpose for the West Virginia Allegheny Highlands Climate Change and Impacts Initiative, but I'm certainly there in spirit. So what I want to do is just to talk a little bit about what is climate change. And if we look at conditions on the Earth is warming. This is very clear. And the climate of the last 30 years has been remarkable in that over this period of time we've seen both increase in the frequency and intensity of extreme weather events, heat waves that have led to the loss of thousands of lives in Central Europe and Russia, increase in the intensity of hurricanes and typhoons, floods around the world, and our best intergovernmental panel on climate change models predict that these types of system responses to global climate change will become more frequent as we go into the future. So if we look at how the temperatures have warmed, these are decadal intervals starting with 1961 to 1970 and coming up to the present. And when you look at these, you can see that as we come into to the future, that the warming has been greatest up in the Arctic because of the loss of sea ice and glaciers in that area, exposing darker surfaces and getting warmer temperatures occurring in that region. If you look at what's happened to sea ice over the periods of those records, you can see that it's been decreasing and that the 2012 minimum was 19% below the previous minimum, which was set in 2007. And I should point out that the loss of that sea ice is much more rapid than any of our models predicted. If we look at the continental U.S., 2012 was the warmest year on record by far, and you can see that in this diagram of all the mean annual temperatures since the turn of the century. And if you look at these, you can see that the warmest, shown in red here, are all in the 1990s or the 2000s, except for 1934 during the middle of the Dust Bowl years. But all the cold temperatures are in the early part of the century or the late part of the last century. So the whole country has been warming over this period of time by about 3.25 degrees Fahrenheit. If you look at this diagram of this man walking his dog, it kind of gives you an analogy to look at climate versus weather. The man would represent climate. He's going in one direction, and his dog, which goes from fire hydrant to piece of paper, back and forth, he's actually a good representation of what weather is. Weather is the day-to-day, year-to-year variations that we see in our climate system, but climate is a 30-year average of that. So if we look in what Mark Twain said, he probably said it best: climate is what you expect, and weather is what you get. And so if you look at Charleston, West Virginia, this past winter, in January, we would have expected, from a climate point of view, to have gotten a mean temperature of 34.8 degrees Fahrenheit. What we actually got, which is weather, it was much cooler, which is 27.7 degrees Fahrenheit. So that distinction is extremely important. If we look at this past January, when we were getting all the cold temperatures in West Virginia and here in Ohio, if you look at the whole world, the red areas, up in Alaska at the same time we were setting record temperatures, and in Greenland, and you have to look at the mean average. So January 2014 was Earth's fourth warmest January on record. So you always have to look globally. So if you look at how these temperatures have been trending down in the troposphere where we live versus those up in the stratosphere, which is the next layer above our troposphere where all of our weather occurs, while the troposphere has been warming, as you see in this lower curve, up in the stratosphere it has actually been cooling, except for the times when we have volcanic eruptions where we put tephra and sulfate into the stratosphere, which absorbs radiation, drives the temperature up there, and down at in the troposphere where we live, temperatures actually drop during those periods of time. So what we see happening in our actual measurements is the response expected from greenhouse gas warming or forcing, and is predicted by the climate models. It is not forced by the sun, because if the sun was driving this, both layers of the atmosphere would be warming equally. So the drivers are human-driven increases in greenhouse gases, and here we're looking at carbon dioxide. Charles Keeling started measuring these back in 1958. They were about 315 parts million by volume. Last year, for the first time in May, we crossed 400 parts million by volume, and this year we crossed that level on March 12th. So not only is CO2 increasing, but there is an exponential rise in the rate of increase. So despite all of our discussions on climate change issues, the basic drivers has not changed. We work on ice cores, and ice cores allow us to look back in time, a very long period of time. And this is a record from Vostok in Antarctica. And in that ice, there are bubbles of atmosphere that trap the greenhouse gases. So we can actually look at how things like CO2 has varied over 800,000 years. And we can look at the temperature reconstructions from that same ice core, and you can see how in sync they are. So during periods where I'm sitting right now was under an ice sheet here in Columbus, Ohio, CO2 was about 180, 200 parts million by volume. But during all the warm periods, CO2 rises up to about 300 parts million by volume. But if you look at where we are now, at 400 parts million by volume, you can see there's no analog to that in this 800,000 year history. And on that trajectory that I just showed you, we are projected to be much higher than that in less than 90 years. And this is really what we're concerned about, because CO2, once it's released in the atmosphere, remains in the atmosphere for decades to millennia, such that 1,000 years from now, the CO2 that we release today, 20% will be still available, and we will be changing the climate of the Earth at that time from what we have already done today. So this is the data from the archives. And of course, we have the models to look at, what's that going to do to extreme events such as temperatures. And so if you look at West Virginia, and if you were to look out at 2040, we would expect to find down in Huntington, West Virginia, 3 times as many 95-degree Fahrenheit days as are now occurring. So those are the drivers. Now, in our group here at Ohio State, we look at ice, and we've recovered cores from around the world to get a global picture of change. And I'm just going to give you a very quick overview of these records. So you can go not only to Antarctica and Greenland, but you can go to the high mountain regions like here in the Andes of southern Peru, and recover an ice core and reconstruct a history of climate from those cores. And this is just an example of our isotope variations, which are our proxy for temperature. You can see every year, this is the period from 1805 to 1825. And in the tropics, where you have a very distinct wet and dry season, every dry season has a dust layer. So by counting these back in time, you have your calendar, like counting tree rings, and you can measure the thickness of those layers and actually get precipitation. Well, we can take all of these records and put them together and look at how temperatures, or isotopes, proxy has changed over the last 2,000 years. So we're going from the time of birth of Christ coming forward, and this is a composite. And when you look at this history, you can see the medieval warm period here, you can see the little ice age in the record, and you can see the warming in the 20th century. And you can compare that to other temperature reconstructions from the northern hemisphere, and you can see the similarities, and this also overlaps with our instrumental record. So what really is outstanding is what's happened in the last 50 years. So, but glaciers also respond to climate change, and I like this quote from Henry Pollack's book, A World Without Ice. Ice asks no questions, presents no arguments, reads no newspapers, listens to no debates, It's not burdened by any ideology, and it carries no political baggage as it changes from a solid to a liquid. It just melts. So the glaciers just sum up what's happening in their environment. I took this photo back when I was a graduate student here at Ohio State. This is 1977. You can see the annual layers on this ice cap. This is the same place by 2002. So you can see that we're losing the history that's in the ice as well as a valuable water resource in this part of the world. If you look at the largest outlet glacier, Korea-Kalis, coming off of that ice field, this is in 1978 from a survey line we have on the ridge above. This is going to fade into 2011. So you can see what the changes have been in this valley over that very short period of time. So these glaciers throughout the Andes are retreating in today's world, as they are around the planet. This is up in southeast Alaska, the Muir Glacier, 1941. This is in August of 2004. So you can see how much ice has melted out of this valley. In today's world, 98% of the glaciers in southeast Alaska are retreating. You got to remember that glaciers are just ice on land. When they melt, they go in the ocean and sea level rises. If you go to the Himalayas, here's a photo from 1921. You can see this glacier coming down, and this is the same valley in 2009. The glaciers studied there, 95% of them are retreating in today's world. In the Alps, there's a similar story. This is a photograph from 1903, and this is what that same area looks like in 2005. 99% of the glaciers in the Alps are retreating in today's world. In Africa, all the glaciers are retreating. The highest mountain is Kilimanjaro. Here's a photo showing where the ice was, the glaciers, in 1912. And this is what it looks like in 2006. The first map was made in 1912. The last map we made was in 2013 of January. And over that period of time, 88.3% of the ice on the mountain has disappeared. 40% of the ice that was present in 2000 when we drilled here had disappeared 13 years later. If you go to New Guinea, there is a glacier, one glacier in the tropical rainforest here. And that glacier also has been disappearing in the 20th century. Here's 1936, 1991, and 2001. And by 2010, when we actually went there to drill, it actually rained every day on this glacier. You can see how much the ice has thinned over that period of time. And in fact, it's only 32 meters thick, and so this glacier will disappear in the next 5 to 6 years at this rate of ice loss. If you look around the world, this is a cumulative picture of glacier loss that's taking place. And of course, as the glaciers melt and temperatures rise, sea level is rising. And this is the history of sea level. Back at the 1900, where sea level was increasing about 0.8 millimeters per year. And you can see in the most recent measured period, we're up to, in 1993 to 2012, about 3.1 millimeters per year. So not only is it rising, it's accelerating as we come into the present. This map kind of shows in red the areas where we're losing ice today on in the world. And so the world's ice cover is responding dramatically to the 20th and 21st century changes in climate. And this has great implications. If we just talk about losing 8% of the ice that's now on land, this is the U.S. Gulf Coast, New Orleans, Miami down here in Florida. If we were to lose 8% of the ice on land, this is what that coastline will look like. So these changes are dramatic, and they have tremendous impacts on humans around the world. And just recently, in the last couple of weeks, there have been a couple of papers come out on the collapse of the West Antarctic ice sheet. And this map actually shows in red the warming that has taken place in West Antarctica versus East Antarctica over the last 50 years based on infrared satellite data and automatic weather station data. But what's really interesting is back in 1978, John Mercer, who was here at what is now the Bird Polar Research Center, wrote a paper in Nature that entitled West Antarctic Ice Sheet and CO2 Greenhouse Effect, a Threat of Disaster. And the two papers that just came out a couple weeks ago suggest that this process is now underway, this collapse is starting, and that it is indeed unstoppable going forward in time. So the really telling, this was the last sentence in that paper, one of the warming signs that a dangerous warming trend is underway in Antarctica will be the breakup of the ice shelves on both coasts of the Antarctic Peninsula, which is up here, starting with the northernmost and extending gradually southward. John Mercer passed away in 1987, but this is exactly what has unfolded in that part of the world. So there's a perfect storm brewing. The ingredients of this perfect disaster are the fact that CO2 has a lifetime over 1,000 years in the atmosphere. There's a climate system inertia. It takes a long time to warm up ice sheets and oceans. There's a positive amplifying feedback. If you melt the ice and the glaciers and the sea ice, you increase the absorption of radiation from the sun, and you enhance the temperature increase. And we have a global fossil fuel addiction. And we could talk about alternative, brighter futures using renewable energies and cleaner air and water, enhanced economic development, and better jobs. But what's really getting people's attention are the extreme events. In 2011, this was Ohio's wettest year on record. And of course, when you get these floods, it costs lots of money. And there is a cost to climate change that we all are now starting to feel. And of course, it's not just here in the U.S., it's global. This is a flood in Pakistan in 2011. And the insurance companies that insure insurance companies globally put the weather-related losses in 2011 at $148 billion, and of which only $55 billion was actually covered by insurance. That means that governments, in our case, taxpayers, and citizens have to pick up that difference. And then the huge storms like Sandy, estimated cost of that one storm is now well over $60 billion. And there's a lot of risk that you don't normally think about. The fact that in New York and New Jersey there are 45 Superfund toxic waste sites within a half-mile of the coast. These become at greater risk as sea level rises and storm surges come further inland. And of course, that same storm, Sandy, brought a huge blizzard in October to West Virginia, in Bellington, West Virginia, seen here. But there's also an increase in the floods in West Virginia. And this shows a flood in Logan in March of 2012. And fires around the country and, in fact, around the world. But if you look at these fires and the acres burned, you can see 2006, 2007, 2012. These are all very recent years where we're seeing this increase in the areas burned by fires. Floods, this was out in Colorado in September of 2013. This is a 1,000-year flood, almost $2 billion worth of cost. People were not insured because it doesn't flood normally in Colorado. And this brings about one of our human natures, that consequences for the individual outweigh consequences for others. So we don't worry too much about if it's people in Bangladesh that are being flooded out, but if that's our home going into the river, then we become very concerned about these changes. Super typhoons, and you see super storms like Sandy and super typhoons have become a norm. This is over in the Philippines, cost over $14 billion in damage. They only had about $2 billion covered by insurance. And then the extremes in weather. This is winter here in the U.S., down in Atlanta in February. But at the same time that we were getting extreme colds in the east, down in Australia they were setting record temperatures, and that's why you have to look at the global average to get what's happening. These are floods this past winter in England. The winter of 2014 was the wettest year on record since records began in 1910, and in fact, by all accounts, this is the wettest it has been in England for over 300 years. So these extremes cost money. And insurance companies mark those. These are weather catastrophes worldwide, 1980 to 2012. You see there's an exponential rise in these. That's very concerning if you're in the insurance business. And but it brings home something that another characteristic of human nature: immediate consequences outweigh delayed consequences. So you can make the argument that we're now seeing the immediate consequences of climate change showing up around the world. So over the last 10 years, weather-related losses have averaged 184 billion a year, of which only 56 billion was actually covered by insurance. So let me close by saying, if I look at our greatest challenges in the 21st century, we will be learning how to get along with each other. And you can debate how well we've done this. This has been with us for a long time. But on top of that, we have learning how to get along with the planet. And these two challenges deal with human behavior. And therefore, they're very closely related as we go into the future. So if we've learned anything from our international space programs, it's how unique the planet is to support life forms that we know and love. And we know that if we were talking about global climate change, that nature's a timekeeper on this. And unfortunately, none of us is wise enough to see the clock and know how much time we have to make the changes necessary to adapt to this changing world. So I want to close with these key points, but instead of going over this, I just want to say that the message today would be that climate change is in the here and now. The extremes in the weather that we have seen will continue to increase, and the ratio that we and you had a couple of years ago in West Virginia, there was just another one of these yesterday down through the south. So these type of events that cause great damage will become more frequent and impact the highlands there in Allegheny. So thank you very much, and again I apologize for not actually being able to be there in person. So thank you.